Hey Sherwood, today we're looking at the mean value theorem from lesson 4.2, and I chose an example on page 202, problem 10 from the homework set. This problem asks us to write an equation for the secant line that joins two specific points on the curve, and also to write an equation for the tangent line that is parallel to that. And in this problem, we're given the equation f of x equals the square root of x minus 1, and we're given a specific interval from 1 to 3. So let's begin by just thinking about what the graph is going to look like. So a square root graph, we know, is half of a parabola. It's like the top half of this parabola. And we're scooting it 1 unit to the right. That's the transformation that x minus 1 produces. Okay. And so here's that half parabola scooted 1 to the right. And let's see what we can do with this here. So when we plug in 1 into the formula, we get 1 minus 1, which is 0. Square root of 0 is 0. So the output is 0. And that explains where that point comes from. When we plug in 3, we get 3 minus 1, which is 2. And you get the square root of 2, which is about 1.414. And that's where that point comes from. Okay, so our task is to find an equation for the line that joins these 2 points. That's called the secant line, since it contains 2 points. And we're supposed to find an equation for which points x, y in the plane are on that line. Well, we can do this by using the slope formula. So if we find the slope of this segment, then we'll know that xy is on this line if its slope matches the slope of this triangle. Okay, so let's see. We're going to do the change in outputs, 1.414 minus 0, okay, which is the square root of 2. And the run, which goes from 1 to 3, the run is 2. So the slope of that segment is rise over run, root 2 over 2. All right, so if this triangle has the right slope, then xy will be on the line. And so let's see what we can do with this. Well, we've got 2 points to choose from. I'll choose the one that looks easier to work with. The point 1, 0 is on the line, and the line has slope square root 2 over 2. So if we just apply the slope formula to these 2 points, then we'll have an equation for the line. Here we go. y2 minus y1 over x2 minus x1 equals the slope. That's the condition we want to achieve. Okay, so this is an equation for the line, and perhaps we'll just solve for y by multiplying both sides by x minus 1. We get the slope times x minus 1 plus 0. So this would be the equation for the secant line. All right, and going back looking at the directions, we just achieved goal 1. Goal 2 is find an equation for the tangent line that's parallel to that line. Okay, so now we would like to find, and I'll clean up the picture, we would like to find a point on the curve where the slope of the graph is exactly parallel to that secant line. Okay, and we'll use calculus to figure that out. All right, before we dig in, let's just step back and think about the theorem that makes this all work. The theorem says that as long as your function is differentiable, as long as it's smooth, as long as it has tangent lines, as long as it has a derivative, then the mean value theorem makes us a promise. Specifically, there has to be some input between the endpoints of the interval where the instantaneous rate of change at that point is exactly equal to the average rate of change over this interval. And our job is to figure out specifically which input makes that happen. Okay. So step 1, we'll find the average rate of change. Step 2, we'll find the instantaneous rate of change. And step 3, we'll make them match. Here goes. So we have the function fx equals square root x minus 1. And since we're going to be taking derivatives, it's helpful to invoke the power rule. So I just wrote that as a power. And we're going to bring this power down and make it a half times the quantity raised to power, which is 1 lower than a half, which is negative a half. And then we apply the chain rule, which tells us to take the derivative of the expression, which is 1. Okay? And so we can now simplify a little bit. We have a half times this. And a power of negative a half is a square root in the denominator. So this right here is the formula for the derivative. Okay. And step 2, now we want to find the instantaneous rate of change of f at input x. And I realize that I just did that. So I've done these directions a little bit out of order. Rather than make a whole new video, let me just say reverse these steps. Okay. All right, so now I'm going to find the average rate of change on the interval. And for that, I need to compute the output of the function at the right endpoint, output at the left endpoint, and then find the difference in those things. This is like delta y over delta x. What's the slope? Okay, well, we saw that when you plug in 3, you get 3 minus 1, which is 2. And when you plug in 1, you get 1 minus 1, which is 0. Okay, and that's where we're getting this value from the previous screen, square root 2 over 2. Square root 2 over 2 is the average rate of change of the function across the interval from 1 to 3. All right, and I've already computed the instantaneous rate of change at value x, but I'm going to do a notation swap. If I take out all these x's and write c's, you can put whatever letter you want. The letters are not important. Then now we've got a formula for the slope at value c. And I do that just to be standard. It's become a convention for people to use the variable c to represent the number within the interval that you're given. The special number where the slope matches the average rate of change is typically called c. All right, so let me see what I need to do next. I need to take the derivative formula, which is here, and I need to find out where that derivative formula is equal to this particular value. So let me write down an equation and then try to solve it. 1 over 2 times the square root of c minus 1 is supposed to equal square root 2 over 2, somewhere. All right, the mean value theorem says it has to happen somewhere, and now we just need to find out where that happens. Okay, so different ways to go about this. Looks like we can multiply both sides by 2 to divide these out, and then I'll bring down what's left. Okay, next step, let's eliminate the square roots by squaring both quantities. And you're going to get this equals that. And now we can just multiply both sides by c minus 1, which is 2c minus 2. Add 2 to both sides, you get 3. Divide by 2, and we found that c is equal to 3/2, or 1.5. Now what does this mean? This is telling us that when c is 1.5, 3/2, that's the particular value, the input, where the instantaneous rate of change or the slope of the graph is going to match the average rate of change, okay, meaning that these two lines are parallel. And so back to the directions, we're supposed to find an equation for the tangent line that is parallel, and that's what we're doing. Okay, so here goes. Step 1 has already been done on an earlier screen, so let me just copy that down so it's organized for you. And I believe I've erased it at this point, so I'll just try to do it from memory. That equation was y equals the slope times x minus the input. From a previous screen, that's the answer to step 1. Step 2, wants the equation of the tangent line that's parallel to AB. And for that, I'm going to need to do, I think, a little bit more work. So in order to get the equation for this tangent line, we'll again choose a point kind of out in the distance and call it xy. And this point right here has x value 3/2, and so we need to find the y value that goes along with that. 3/2 minus 1 is 1/2, and the square root of 1/2 is what it is. It's the square root of a half. So this has x value 3/2 and y value square root 1/2. And so again, we can use the slope formula to find the equation of this line. Okay, so if xy is on that line, then it should satisfy the slope equation, y minus y1 over x minus x1 equals the slope. And again, the slope is square root 2/2. Okay, and let's go ahead and just multiply both sides by x minus 3/2. And we can go one step further. If we want, we can add a square root of a half to both sides, and you get the square root of a half plus all this other stuff. Okay, square root of a half plus all this other stuff. Here it is all in one screen. The equation of the tangent line that's parallel to this secant line is square root 1/2 plus square root of 2/2 times x minus 3/2. And there you go. Problem solved. Okay, let's just go one step further and check our work using technology. Since that's available to us freely, we might as well make use of it. Okay, so here's the formula typed in. Here's the input-output pair when x is 1, input-output pair when x is 3, and there you have the two endpoints right there. Now let's actually make use of our work. And can I type in this equation right here? Y equals root 2/2 x minus 1. Root 2/2 times x minus 1. And let's check our work. Did we get the equation right? We did! That line is indeed passing through the 2 points we were given. So that was the correct equation. And I can even restrict that so that it only goes from 1 to 3. And now you see just the segment that connects those 2 points right there. That's the secant segment. All right, so that indicates that we did this work correctly. Now let's go to the tangent line, and I'll type in this equation, square root of a half. All right, the square root of 1/2 plus square root of 2/2 times x minus 3/2 square root of 2/2 times x minus 3/2. And there we can see the blue line appears to be parallel to the red segment, which is a good thing. And let's do one more thing, which is to type in the special input. All of our work was pointing towards this conclusion right here, where we showed that the important value in this problem is 3/2. All right, so I'll type in 3/2, and let's ask for the output that goes along with that. Okay, and there you see that purple dot has x value 3/2 and y value square root of that minus 1. Okay, so we're hitting the target point, and our slope appears to match, so everything checks out. All of this confirms that our work is correct, and so we can call it a day. I hope that this video has helped you to understand the mean value theorem and apply it to solve problems. See you next time.